This is the second semi-annual progress report on the Airborne Optical Adjunct project as of February 1987. This project is managed by the Airborne Optical Adjunct Project Office of the U.S. Army Strategic Defense Command in Huntsville, Alabama. Prime contractor is Boeing Aerospace Company, Seattle, Washington. The Airborne Optical Adjunct is a key element in the U.S. Strategic Defense Initiative research program. AOA is a technology validation experiment. Its purpose is to experimentally validate the real-time ability of a long-wavelength infrared optical sensor and a data processor on an aircraft to acquire, track, discriminate, and then hand over data on incoming ballistic targets to a ground-based radar. The capabilities of the integrated subsystems and related software will be experimentally validated with a series of actual flight tests. The Boeing 767 airplane that will be used for the AOA experiment is owned by the Boeing Commercial Airplane Company and is provided at no charge to the federal government. It is the first production 767 built. Atop the airplane's forward section will be attached an 86-foot-long cupola, about 10 feet wide and 8 feet high. Inside one of two 16-foot-long modules inserted in the cupola will be the long-wavelength infrared optical sensor, which will look through an open viewing port on the left side and traverse back and forth as it moves along tracks on the floor. The sensor control console will be installed in the main cabin, as will be the sensor signal processor, analog equipment, and support equipment. Likewise, the data processor and its associated control and display console and other communication, navigation, and recording equipment will be installed in the main cabin. In addition, items such as cryogenic cooling systems and environmental controls will be stored in the cargo bays. All told, an additional 39,000 pounds will be added to the airplane's weight. Boeing is responsible for modification and flight testing of the 767, construction of the two modules, hardware installation and integration in the mission support van, integration of all AOA air and ground systems, including communications, and development of the unique algorithms which will enable the AOA computer systems to fulfill mission requirements. Late in February 1987, Boeing Commercial Airplane Company released 767 VA001 from its flight test program and turned the aircraft over to the AOA project. Symbolically, the airplane key was passed from the Boeing Commercial Airplane Company to Boeing Aerospace Company to the Strategic Defense Command. The airplane was positioned in the hangar at Boeing's Seattle Flight Test Center, and the erection of work platforms was the first visible sign of the start of modification. The forward and aft fairings of the cupola will be secured to frames fastened to attach angles, which will be bolted to the airplane around the cupola's periphery. Each of the two removable modules will be mounted on the exterior of the cabin pressure shell. The modules are in work at nearby Boeing Plant 2. The first frame of the first module was bolted into place on February 3, 1987, an AOA milestone. 3 weeks later, the module was taking shape. A dummy sensor is being built for the module. With foam blocks fastened to this framework, basically, the dummy sensor will be the same size and shape as the Hughes sensor. In airworthiness tests prior to installation of the flight sensor, the dummy sensor will be propelled back and forth on the rails of this module with the module viewing port open to obtain in-flight data on the airflow inside the module. The data will validate wind tunnel tests, which determine that by blowing air across the open port and circulating air inside the module, the turbulent effects of the outside air rushing past the module's open port would be neutralized. The Hughes flight sensor will go in the next module to be fabricated, now in the early stages of construction. In the foreground here are the floor beams for the second module. Hughes Aircraft Company, the AOA sensor subcontractor, is continuing to make significant progress in fabricating the AOA sensor. Hughes' goal of delivering the sensor to Boeing, Seattle, on the original target date, November 2, 1987, remains unchanged, despite technical problems encountered since the initial report in this series. Most of these problems have been resolved, and a schedule and a plan supporting the November delivery date have been developed. Hughes technicians are assembling and testing hydraulics and servo motors that will move the sensor's telescope in elevation and azimuth and power the sensor along the rails. Here, the inner gimbal assembly is under test. As for the outer gimbal assembly, the azimuth ring assembly, including the azimuth drive subassembly, has been mated to the truck assembly, and servo testing has been completed. A delay in the timetable for the focal plane array resulted when noise and crosstalk problems were discovered. The focal plane array is the heart of the sensor. It contains thousands of tiny detectors similar to the rods and cones on the retina of the human eye. They respond to infrared energy focused on them by the telescope mirrors. Data from these detectors flow through a signal processor, which converts the analog information to digital form for the data processor. The 15-inch long focal plane array will contain 15 sensor modules, each with 4 sensor chip arrays made up of 640 detectors each, a total of 38,400 detectors in all. Testing of the sensor modules at each stage of their assembly is performed at the Hughes Microelectronics Center in Carlsbad, California, by advanced automated test equipment. Validating the test stations, both for the sensor chip arrays and the sensor modules, took longer than anticipated, but validation now has been achieved. Hughes Santa Barbara Research Center, which assembles the sensor chip arrays and the sensor modules, made several wiring changes in the modules. Electromagnetic interference was overcome by installing 11 bypass capacitors on each module. Final acceptance of the first flight module was completed in late February 1987. 15 flight modules are required along with 3 spares. A sufficient number of sensor chip arrays has been selected to fill all flight modules. The ability to search out and eliminate the noise and crosstalk was a direct result of previous experience with other sensor programs. Dealing with the difficulty at this stage of the AOA project, rather than later after assembly of the sensor, avoided a major schedule slip and serious future problems. Early testing of sensor chip arrays showed good results with 2 of the 3 AOA bandwidths, short and medium. Recent efforts to increase the performance of long band arrays have produced favorable results, indicating that they will fully meet requirements. Scheduled recovery date for final assembly of the focal plane array is May 9, 1987. On May 23rd, the focal plane array will be delivered to Hughes System Integration and Test Laboratory. The optical portion of the AOA sensor program is virtually on schedule, despite the fact that the initial secondary flight mirror was damaged and had to be replaced. A new secondary mirror was completed by Tinsley Laboratories of Richmond, California, builder of all 3 of the aspherical fused quartz mirrors used in the sensor. Coating of the new secondary mirror by GM Vacuum of Newport Beach, California, was completed late in January 1987. The flight primary mirror was finished late in February. Prior to that, however, the flight optics bench was assembled by installing the flight tertiary mirror, shown here, the warm test primary mirror, the test fold mirror, and the repaired secondary mirror into the beryllium optical bench. The first phase of warm alignment Aligning the mirrors at room temperature was completed in mid-February. The bench then was disassembled and reassembled with the remaining flight mirrors. Warm alignment with the flight mirrors will continue for several weeks. In early May 1987, after a special test focal plane array has been installed in the telescope vacuum housing, final alignment of the mirrors will be performed at the cryogenic temperatures in which the system will operate. The flight focal plane array will be installed in late June 1987. The flight unit of the inertial angular reference system, one of the most critical elements in the sensor, has arrived at Hughes. It was hand-carried to Los Angeles from the Honeywell plant at Clearwater, Florida, where it was assembled. The system's ring laser gyros provide pointing and stabilization control, enabling the sensor to point with the precision necessary to satisfy AOA requirements. Honeywell's Space and Strategic Avionics Division at Clearwater not only builds the inertial angular reference system under contract to Hughes, the company also is a subcontractor to Boeing to provide the AOA onboard data processor. Honeywell engineers faced a major task in designing a data processor powerful enough to meet AOA computing requirements, but small enough to be accommodated in the testbed airplane. In constructing the electronic boards for the data processor's flight hardware, engineers discarded ordinary soldering techniques in favor of a method known as vapor phase soldering. This was necessary to achieve the desired high reliability and repeatability between the flat packs and the printed wiring boards. As a result of this and other advanced techniques, Honeywell has produced an AOA flight node only 30 inches long, 12 inches wide, and 9 inches high, and weighing on average about 130 pounds. Yet each flight node is capable of processing approximately 3 million instructions per second. Here, 7 of the 10 flight nodes being supplied for the AOA project have been installed in the flight rack in preparation for a 9-node bus test. 9 nodes will be utilized during the Kwajalein Atoll flight tests. The 10th is a spare. 5 flight nodes were delivered in place at Clearwater late in January 1987. Another node is undergoing acceptance tests after replacement of an integrated circuit. The first 4 flight nodes delivered to Boeing Seattle slightly ahead of schedule were returned to Honeywell Clearwater for retrofit. That job is ahead of schedule. When returned to Boeing Seattle, the first 4 nodes will be integrated with the 5 developmental nodes also built by Honeywell. In the meantime, software designers at Boeing continue using the developmental nodes as a test bed to implement and test Boeing-developed algorithms for measurement processing, scan-to-scan correlation, precision tracking, and handover prediction. These algorithms are expected to meet or exceed all requirements. From this test bed, the algorithms will be coded into real-time software and distributed across the 9-node flight architecture. The new 1861 building at the Boeing Aerospace Center near Seattle houses Tempest-accredited facilities, which will play key roles in final preparations for the AOA experiment. In this area of the just completed System Integration Lab, a full-scale cabin mock-up of the Testbed 767 will be constructed. Before it is put aboard the airplane, the main cabin flight hardware, including the sensor signal processor, the data processor, actual flight cables, associated control and display consoles, every AOA mission unit that interfaces with the sensor will be installed in the mock-up. Checkout and integration of those systems is set to begin June 1st, 1987. Following its scheduled November 2nd arrival, the sensor will be moved to the System Integration Lab and placed on the floor of the flight module. The module base will rest on a seismic slab. The sensor subsystem will be reassembled and tested with the mission sensor control console. With the cover of the module still removed, the performance of the sensor's inertial angular reference system will be measured with a twin-axis laser goniometer while the system is tied to the mission recording system. After that, the sensor will be moved into the calibration chamber briefly for a fit check. Once that is accomplished, the sensor will be transported back to the System Integration Lab. The cover will be attached to the module and the interior clearances checked. Coolant from nitrogen tanks alongside the building will take the module interior down to 55 degrees below zero Fahrenheit. This is typical of the environment in which the sensor will operate when the viewing port is open during the Kwajalein Atoll flights. After that, the sensor will be linked with the remaining mission equipment in the 767 cabin mock-up, as well as the mission support van located near the building. Integration tests will continue until all objectives have been achieved. Then the module with the sensor inside will be transported to the AOA 767 for the start of flight tests, to be confined initially to the continental United States. Original plans called for calibration of the sensor prior to flight testing. The revised schedule provides for calibration after completion of some of the continental U.S. flight tests. A May 9, 1988 deadline has been set for completion of the sensor calibration. This procedure will take place in the infrared calibration chamber being installed adjacent to the System Integration Lab. Boeing is investing approximately $44 million of capital funds for the facility, the largest of its kind in the world. The contractor, Pittsburgh Des Moines, is in the process of completing the steel housing for the chamber. Plumbing is being installed, and leak tests are underway to determine that a vacuum can be drawn. At mid-year 1987, Perkin-Elmer Corporation will commence delivery of the sophisticated optical elements which will adapt to the government-furnished calibration chamber and its precision black body source, traceable to the National Bureau of Standards. The delivery is under a new schedule specifying completion of the infrared sensor calibration chamber by the 15th of February 1988, a date which supports the AOA test program. Much of the electronic and communications gear for the mission support van is in place and operational. Still to be installed are 2 computers, including one for a graphics display. After a 3-month test period, the mission support van will be linked to the System Integration Lab for the start of integration tests June 1, 1987. The van will be flown by U.S. Air Force C-141 aircraft to the U.S. Army Kwajalein Atoll for the AOA flight tests there. To make sure the flight goes according to plan, Air Force personnel at nearby McCord Air Force Base had a pre-mission exercise. The 45-foot-long van was loaded aboard a C-141 cargo plane. The empty weight for this loading was about 23,000 pounds. Fully loaded, the van's weight will be approximately 32,000 pounds. The van was secured according to Air Force standards and now has been certified for air transport by Wright-Patterson Air Force Base. Although this loading involved a C-141, the van can also be shipped on a U.S. Air Force C-5 cargo aircraft. The flight test program will be conducted over the U.S. Army Kwajalein Atoll in the Central Pacific in 1989 by the government and Boeing test team. In a typical scenario, an ICBM will be launched from Vandenberg Air Force Base, California, some 4,200 nautical miles northeast of the Kwajalein Atoll. 5 to 10 minutes after launch, the ICBM releases its re-entry vehicles and penetration aids, such as decoys, which travel on a ballistic course above the atmosphere. As they approach Kwajalein 20 to 30 minutes later, they re-enter Earth's atmosphere in the terminal phase of flight. The sensor, scanning through its potential field of view, detects the re-entry vehicles at long range by their infrared emissions against the cold, dark background of space. The onboard data processor will distinguish among a multitude of objects, some detected by the sensor, others injected as simulated ballistic targets into the data processor. Here, for example, a re-entry vehicle, shown near the center of the upper picture, is color-coded red. The other objects are stars, decoys, space junk, or unknowns. The data processor's logic will categorize everything on the screen while precisely determining and predicting the trajectory of each moving object. The processed data, including target discrimination and projected tracks of selected targets, will be passed via a communication satellite to a ground terminal and a ground-based radar on the Kwajalein Atoll. This second semi-annual technical progress report on the Airborne Optical Adjunct has covered the period from August 1986 through February 1987. Major coming events include completion of modification of the AOA 767, completion of both flight modules, final assembly of the sensor's focal plane array, the start of integration and checkout in the Boeing System Integration Laboratory, achievement of flight software integration, and delivery of the sensor to Boeing Seattle. Participants in the AOA project have faced many challenges in recent months, but the AOA team of Boeing, Hughes, Honeywell, and the government have worked together to meet these challenges. Key management positions have been strengthened, management controls have been tightened, and recovery plans have been established and are being monitored closely. As an example, the AOA team has integrated the Boeing and Hughes integration and test organizations. This has reduced the schedule risk. Admittedly, the schedule is tight, but given the dedication of the AOA team, it is doable, and it will be done.
Despite the political changes occurring around the world, the long-range strategic threat remains real. The economic turmoil in what used to be the Soviet Union is casting real doubt on the future of thousands of ex-Soviet ICBMs. Another threat is typified by the Scud missiles used by Iraq during Operation Desert Storm. Medium and short-range theater missiles are becoming increasingly available to governments which are, or may become, hostile to the United States and its allies. The ability to quickly detect, identify, and track incoming warheads is essential for an effective missile defense, a task made even more difficult by the use of missiles containing multiple warheads and decoys. The Airborne Surveillance Testbed, or AST, is a key resource in the Strategic Defense Initiative Organization's ongoing development of effective missile defense systems. The AST uses a passive infrared sensor and high-speed computers to first detect and then track ballistic missile targets at very long ranges. As the targets approach re-entry, discrimination is performed to identify and differentiate warheads and decoys. The target track information is then handed over to ground-based radar stations. The modified Boeing 767 carries the Hughes Wide Field of View optical sensor to an altitude of 45,000 feet. This puts it above almost all weather and atmospheric distortion that can mask incoming objects from sensors operating at lower altitudes. The AST has an outstanding record of success, gathering valuable target data on 11 missions to date. A typical mission was Firebird, flown in April 1992. A Talos Ares missile containing target objects and decoys was launched off the east coast of the United States. The AST acquired the Ares second stage booster and payload bus combination 83 seconds after liftoff. Real-time tracks were established on the second stage booster and the separated payload bus and nose cone halves prior to payload deployment. The AST detected the deployment of the decoy balloons and, as predicted, resolved them as separate objects. All the objects in the target complex which now consisted of the second stage, the payload bus, and the two balloons, were continuously and simultaneously tracked. The missile continued to deploy test objects. The AST's passive infrared sensing system successfully detected the new decoys and continued to track the target complex. The AST successfully tracked the target complex, which now included the second stage, the payload bus, the two balloons, and the three decoys, throughout their trajectories for approximately 10 minutes. Data were collected continuously until the target's demise as they re-entered the Earth's atmosphere. The AST is the most capable wide field of view system for acquiring the infrared signatures of endo- and exo-atmospheric objects, and for demonstrating key surveillance sensor functions in real time. The value of a continuing AST program is threefold. First, the target signature data it's collecting is critical to the design of SDIO elements. Second, the AST has proved to be a reliable surrogate for national missile defense sensors still under development. In its surrogate role, the AST will fill in for these sensors in SDIO systems tests. Third, the mobility of the Boeing 767 platform and the capability of the Hughes sensor make the AST a valuable resource for exploring the development of theater missile defense elements. So far, the AST's missions have involved tracking and collecting data on missiles such as Minuteman III and Peacekeeper, as well as specially designed test vehicles. The AST will continue to measure signatures on new and more complex decoys, as well as participating in experiments with other missile defense system elements.